mathematics, greatness is measured by the problems you solve. And 20 years ago, one person solved one problem that made them immortal. That person was Andrew Wiles. The problem was called Fermat's last theorem, and the story of how he solved it is inspirational. So to celebrate the anniversary, I've invited a new generation of maths prodigies to hear and help tell the story.
Wanting to do something like prove Fermat's last theorem, it's very ambitious.
It's actually a really nice problem. It's really easy to understand, but it's like really hard to solve.
For several hundred years, the great minds like Gauss, Euler, they tried to attack this question, but they had no clue where to start.
Hands up if you've spent more than a day on a maths problem. A month? A year? Well, there's one guy that beats everyone. It's this guy here, Andrew Wiles. Wiles was born in the United Kingdom in 1953, but the path his life would take was paved much earlier. It all started in the 17th century, where amateur mathematician and genius Pierre de Fermat was thumbing through his copy of an ancient text, the Arithmetica. The book contained mathematics that were centuries old, but in the margins, Fermat wrote equations that were new, astonishingly new. But it wasn't until his death that anyone actually discovered any of this great work. And he never left a proof for any of these awesome discoveries. That was left to the reader to work out for themselves. It was as if he'd published his own Lonely Planet guide to maths. And so what he was doing was saying, hey guys, take this book and you can find out all these great places you can go and visit. But there was no directions. There was no way to get there. So people worked out how to get there. They made up their own proofs. And all of the notes got proofs, except one. It was the last one. It was Fermat's last theorem.
People started to doubt whether it was actually true, and others thought that maybe Fermat made a mistake.
The best mathematicians tended to think that the proof was not going to be accessible anytime soon because there was no obvious way of attacking the problem, no way of saying, okay, we're going to apply specialized techniques X to this problem.
And after a few hundred years, they just abandoned the question and went for something more mainstream.
At least until a young Andrew Wiles discovered it in the 1960s.
Andrew Wiles was 10 years old and he was in a local library and he found a maths book
with Fermat's last theorem inside it, and he was just really intrigued by this question because he could understand it.
And from then on, he made it his dream to attack this problem and eventually find a solution.
So what was Fermat's last theorem? Well, it begins with something we're all taught at school, Pythagoras' theorem.
So Pythagoras' theorem states a squared plus b squared equals c squared. And Fermat's last theorem extends that, swapping the squared into any whole number bigger than 2. It could be 3, 4, 5, any number all the way to infinity, and there'll be no possible whole number solutions to that equation.
That's odd. Why should that be the case? That's a pattern. There should be a reason for that. So anyway, he goes and says, I'm going to try and solve it. But the problem was, the world that he was dealing with, the world that was described in Fermat's Lonely Planet, that had changed. In the 1950s, mathematics had become very strange. Fermat's Lonely Planet guide was now just a chapter in a much larger book of discoveries, The Hitchhiker's Guide to Euclidean Space. And worse still, mathematicians had found other spaces that were so radically different from one another that they needed hitchhiker's guides of their own. In the pages of The Hitchhiker's Guide to Projective Space existed objects that were embedded on the surface of spheres, called elliptic curves, while The Hitchhiker's Guide to Hyperbolic Space detailed objects that walked away with negative curvature that you couldn't even visualize. These were called modular forms. And so modern mathematics didn't seem to have anything to do with Fermat's last theorem. But the eventual answer to Fermat's last theorem came from just such an unlikely connection between the two radically different spaces. Two Japanese mathematicians, Taniyama and Shimura, made a suggestion that no one believed. They said that any elliptic curve using whole numbers or fractions was actually a modular form in disguise. But what the heck did that mean? Well, elliptic curves are a lot like the seam on a tennis ball. They're created by projecting a curve from the plane onto a sphere so that the points at infinity meet up to form a closed loop. But a modular form is a completely different beast. Being modular means that there's a regular pattern that extends out in all directions of hyperbolic space. To get your head around it, in regular space, it looks like this. One bit that's actually repeated indefinitely. So what were Taniyama and Shimura actually saying? They were suggesting a connection between the two objects. They said, without bending or warping, you could always slot the infinite pattern of a modular form through the closed loop of an elliptic curve. Much like a coil can slot through a circle, but only if the elliptic curves were generated by whole numbers or fractions. So what did this have to do with Fermat's last theorem? Well, nothing. It wasn't until a long time later that this guy came along, Frey. I love this guy, Frey, because he came into Taniyama and Shimura in the 80s and he changed everything. Frey considered the unthinkable. What if Fermat was wrong? What if you could find whole numbers that fit the equation for powers higher than 2? Well, if such a solution existed, Frey created an elliptic curve that turned out not to be modular. But Taniyama and Shimura said every elliptic curve generated by whole numbers had to be modular. So that meant there was a link between the two. If Fermat's last theorem was wrong, so was Taniyama and Shimura. But if Taniyama and Shimura was right, then you'd finally prove Fermat's last theorem. And of course, who was interested in that? This guy. Andrew Wiles was ecstatic. Finally, he had a way to actually prove his childhood dream. He'd converted a 350-year-old problem to only a 30-year-old problem.
Basically, Wiles decided that he would start working on the Taniyama-Shimura conjecture in order to prove Fermat's last theorem.
He worked in secret and without his peers knowing.
He was working on the same problem for 7 years, not knowing that he would even necessarily ever be able to solve it.
That would be something just out of someone's mind to do.
It's just an astonishing level of commitment.
So how did he do it? Well, if I could tell you in a few sentences, it wouldn't have taken him 7 years. But basically, it was a counting argument. He was able to work out how to convert elliptic curves into modular forms and vice versa, but he didn't know whether he had the same amount after doing that process. So he counted them. But that's hard to do, because there's infinitely many of them. And that's what he worked out. He worked out a way to actually count infinite sets. And he got there. Wow.
It's just amazing.
To have worked on it for so long, I really think that he deserved to achieve his childhood dream.
He's one of the few mathematicians who's managed to solve something famously hard, which is obviously what we'd like to do if we could manage to do it, which is probably not going to happen, but it's worth a shot.
So he solved his problem. Fermat's last theorem was finally solved. But don't worry, there's still unsolved problems that you could solve. So get cracking and solve some problems, because immortality awaits, people.